Now after stating this elementary matrices, what are these? Let me go a bit down and let me take another thing. Let me take an example. So here I will take an example. And as example, I will take a matrix. Suppose the matrix name is A, and that's equals 3, 5, 6, 7. And suppose that to this matrix we will apply an elementary transformation, and the elementary transformation is R1 interchanged to R2. Please note that from here onwards we'll be using only the row operations and not the column operations. So there will be no use of column operations, but instead there will be only use of row operations. So we are applying R1 interchange to R2. So the matrix which will obtain will be B equals, this will be 6, 7, 3, 5, because this R1 will be interchanged to R2. That is one side. Now on the other side, what we do, we will take an identity matrix of the same order. If this is 2 cross 2, we will take identity matrix of the same order 1, 0, 0, 1. Now to this identity matrix, what we do, we will apply the same transformation. So we will apply R1 and R2, and suppose that the resultant matrix which we get is I dash, and let that be, let me keep it a big dash, this will be 0, 1, 1, 0, because we are interchanging the row 1 and row 2. Now the question here is there any relationship between this I1 which we obtain after perform the this operation to I, and the matrix B which is obtained from A by performing the same operation? The answer is yes, of course they have a relationship. And what is the relationship? The relationship is just like this. Now if I take this I dash and we prim multiply it to A, we take I dash A, that will be same as I dash is 0, 1, 1, 0, and A is 3, 5, 6, 7. When you multiply it, we see that the result which we are getting is 0, 3 is 0, 1, 6 is 6, 0, 5 is 0, 1, 7 is 7, 1, 3 is 3, 0, 6 is 0, 1, 5 is 5, 0, 7 is 0, so here is 5. So we are getting 6, 7, 3, 5, which is same as B. So from this, what we got is that if we have any matrix A, we apply the row transformation. I am repeating again and again, we are only applying the row transformation, not the column transformation. So we are applying the row transformation. We are getting the resultant matrix B. On the other side, if we are taking the identity matrix and applying the same transformation to that matrix, we are getting some resultant matrix I dash. And if we prim multiply this I dash to this A, then that gives us same as this B. So doing any row operation to this A is same as perform the same row operation to I, and whatever matrix we are getting from there, just prim multiply it to A, we will get the matrix which we would have obtained by applying the same operation to this matrix A. So let me explain this again. Given a matrix A, performing any row operation, again I am giving stress to row, we are performing only row operation, performing any row operation to this matrix is same as perform the same row operation to identity matrix and multiplying this resultant identity matrix which we have got for identity matrix to A, but we have to prim multiply it. This resultant matrix will be same as we would have got by applying the same operation to this A. With this observation, we come to the following theorem. Let me go a bit up. Let me rub out this elementary transformations here, or elementary matrices here. Let me rub out this. So we have the following theorem here. Here the statement of the theorem. Let E be the elementary row operation and E be the corresponding elementary matrix then applying this elementary transformation to A, any matrix A, is same as just performing this elementary matrix which we have got by applying the same elementary transformation to identity matrix by multiplying this E to A. I will repeat it again. Performing this elementary row operation to I, we will get E, the elementary matrix, and if we perform this same operation E to A, that is same as multiplying this A by E, which we read in the previous example. See, we had in the same thing in the example. The I, this is the elementary matrix, multiplying the elementary matrix to A is same as the operation to this A. For this theorem and a proof of the theorem, you can look at the linear algebra by Sherman's outlines and page 87. Note that if we would have applied the column transformations, then the result would have been something different. That it would have been, suppose F is the column transformation, then FA would have been A, and this F, where the capital F would have been the corresponding elementary matrix. So that's why we are applying here only the row transformations and not the column transformations. Final thing which we need before starting finding inverse by elementary transformation is the following. Let me go a bit down. So for that, let me take a matrix here. Let me take 3, 5, 6, 7, 1 matrix, and let me take another matrix as 9, 10, 11, 12. Let this matrix be the matrix A and this matrix be the matrix B. Now, if I apply the transformation, I will apply the simplest transformation, but note that we are only applying the row transformations. So I will apply row 1 to row 2. Just interchange row 1 as row 2. The question is, if I interchange row 1 to row 2, what will I get? The first part is, shall I interchange row 1 to row 2 in both the matrices A and B, so that I can get here 6, 7, 3, 5, and this will be 11, 12, 9, 10. Shall this interchanging row 1 and row 2 means that I have to interchange row 1 and row 2 in both A and B, or will it mean that we have to interchange the row 1 and row 2 to only one? Let it be A here, so it is 6, 7, 3, 5, and keeping B silent as it is, so B is 9, 10, 11, 12. And the third part is the third part, or shall this or will this A remain same as it is and B will change. So the third part is, will it be like 3, 5, 6, 7 and 11, 12, 9, 10. So in order to see which one among these three is true, let us go back to theorem which we earlier read. So for that, let me do one thing. Let us take the corresponding identity matrix of the same order. Let me take I equals 1, 0, 0, 1. And let me do the same transformation applying R1 as R2 for this. So we are interchanging R1 to R2. So what will we get? We will get I dash. Let me have different color for this. So we will get, let us name it as I dash, that will be equal to, that will be 0, 1, 1, 0. So let me take the help of the previous theorem. The previous theorem says that whenever we do an elementary row operation, then doing the elementary row operation to any matrix is same as multiplying that matrix with the elementary matrix. So in this case, this is the elementary matrix I dash. We can name it as E, the elementary matrix E. And the operation is we are interchanging R1 to R2. So if we multiply this E to this matrix AB, which is actually a product of two matrices and hence will give a single matrix, then whatever we will get among the three will be the required answer. So let us multiply this and we will see which one is the required answer. So if we have EAB, let me have different color for it, that will be equal to E is 0, 1, 1, 0, A is here 3, 5, 6, 7 and B is 9, 10, 11, 12. So if we multiply it, we multiply this to this matrix, we will get 6, 7, 3, 5 and 9, 10, 11, 12. So that means this second part is the right one. So this means that whenever we have product of two matrices A and B, and we are doing a new row operation, I'm again saying we have to do a row operation or a column operation. Then in the row operation, the first element will change according to this operation, the first matrix, and the second matrix will remain same as it is. The reason being that the application of any row operation is same as multiplying the given element by the corresponding elementary matrix, and the elementary matrix is we have to pre-multiply. So when we pre-multiply it, it will just change this A, not this B. So with this, we are now ready to take our final topic, which we actually have to take, that is finding inverse of a non-singular matrix using elementary transformation or operation. So let me rub out this hole. So now for this, let me keep it in this way. Note that the previous example gives us the answer why row operation effect is a pre-multiply, that means the first matrix of the product. And you know now the reason being that, and the row operation on the product means that we have to pre-multiply it by the corresponding elementary matrix, and that will affect the first multiply only, the pre-multiply only, not the second matrix. So with this, we are now in a position to take the topic finding inverse of a non-singular matrix using elementary transformation. We know that any matrix A can be written as IA. If we consider a matrix A, then this A can be written as IA. Now, if we do the elementary transformation but only elementary row transformation to A so as to reduce A to I, then this I will be reduced to some B. Since we will be considering only row operations, so the row operation will not affect the post multiply, it will affect only I, and I will change into some other matrix B, and this A will remain same. So AB will be equal to I. But we know that the definition of the inverse of matrix, whenever AB equals I, this B has to be the inverse of A. So this B we will get to be A inverse. So this is it. We take A is equal to IA, do the row transformation so as to reduce A to I. This I will reduce to some B and then A, and this B will give us the inverse of A. In order to understand it better, let's consider an example. So let me go a bit down and let me take a 2 cross 2 matrix, and let us consider a matrix A equals 1 3 2, suppose this is 3 again, and we have to find inverse of this matrix using the elementary transformations. So the thing is that we have to write A equals IA, which implies A is this 1 3 2 3, that's equals I will be the corresponding 2 cross 2 identity matrix. A will remain same because we will be considering only the row operations, and hence that will affect only this first matrix, which is the identity matrix, and this A will remain the same. Now, in order to make the identity matrix, we will first make this 0. Let me have a different color for it. We will first try to make first this 2 equal to 0 by using this row 1, then make this 3 equal to 0 by using this row 2, and then make this 1. So we will first attack this 2. In order to make this 2 0, let us apply since this 2 is in R2, so let's apply to R2 minus 2 times R1. So as I apply it in this way, what will I get? So we get, this will be 1 3 will remain as such because we are doing all the operations to R2, and R2 will change to R2, which is 2 here, minus 2 times R1, this 2 1 that is 2, and R2 is again the corresponding element 3 minus 2 times 3, which is 6. That's equal to the same operation will affect this I. The first row will remain same. The second row will be R2, which is 0 minus 2 times R1, which is 2 1 0 is 2, and 1 minus 0, and then A, which is same as 1 3 0 minus 3 equals 1 minus 2 0 1 and A. Now make this 3 0 because I have to make it identity by using R2. For that, let me use from here a different color. We will apply R1 as R1 plus R2 because this R1 plus R2, if I applied it to R1, this will be 3 plus minus 3, that will give me 0 here. So I have to make this 0 by using this R2. So what will I get? So we get since I am applying everything to R1, so R2 will remain as such, 0 minus 3. R1 will change, this is R1 plus R2, it will be 1 plus 0 will be 1, this will be 3 plus minus 0, that will be 0, that's equal to, same thing will apply here also, minus 2, 1, and this will be here minus 2 plus 1, that will be minus 1, and 0 plus 1, that will be 1, and then A. Now I have to only make this one to get this identity, and as I make this matrix identity, this will reduce to A inverse. So for that, let me go a bit down, let me rub out this. For that, I have to make this one. In order to make this one, I will divide this R2 by minus 3. So I will apply R2 as R2 divided by minus 3, so as to get, now the R1 will remain same, 1 0, as we divide minus 3 to 0, it will remain same as 0, as we divide minus 3 to minus 3, it will go to 1, that will be equal to, this will be minus 1 1, minus 2 by minus 3, and 1 upon minus 3 into A. So this matrix which we obtain, let me name this as A inverse. Now this into A gives identity, and therefore by definition this matrix has to be A inverse. Therefore A inverse will be equal to minus 1 1, 2 by 3, and minus 1 by 3. So this is it. You can take some more examples at your home and practice them. Note that if you have any 3 cross 3 matrix, let me take a general 3 cross 3 matrix. Let it be suppose some A, B, C, D, E, F, G, H, I. Then do one thing. First make this D and this G 0 in a single transformation, and in order to make this 0, use this row 1. Use R1 to make these two zeros, and then attack this edge. This is the first step. You should follow step 1, and this will be step 2. Make this edge 0 by using this row 2. Using row 2, and then make this 1. This is step 3. And then in a single transformation, make this F and this G 0. So this will be step 4 by using this row 3. And finally make this 0 by using, this is step, this is just step 4, this is step 5. Make the 0 by using R2, and make these two ones if needed. So this procedure will give you the identity on the right hand side, left hand side, and the right hand side matrix will give the A inverse in case of 3 cross 3 matrix. So you can take many examples and you can practice them at home. So this was it for this video. In the next videos we shall be coming up with more interesting topics and in more interesting way. For that, stay tuned to our channel and do not forget to subscribe. Thank you.